Hello everyone. So far we've seen ISA specifications and various trade-offs. So this is the first lecture on the microarchitecture, implementation of microarchitecture given the specific ISA. So it's, as I said, time to implement the given ISA. In today's lecture, we'll start discussing microarchitecture concepts, particularly known architectural difference is based on the single count for cycle count for executing the most time-consuming operation. The execution might take a single cycle or multiple cycles to complete in general. In order to talk about the details, we needed to pick one of the toy architectures, and I voted for the microarchitecture of our book by Dr. Mano and Kime. So their architecture is a load store type and might well serve as a nice framework for designing a detailed or sophisticated processing logical unit. So in our first session, we'll focus on single cycle machine, and the subsequent session will be mostly based on multi-cycle microarchitectures, as well as different types of control logic design. So there are two major building blocks of a CPU. These are called Datapad and control unit. Datapad is responsible for all the data manipulations, which include register transfers, arithmetic or logic operations on the register stored values. It also has a set of control interfaces, which are quite design specific. Control unit is basically the combinational or the sequential circuit that produces the necessary control signals for the datapad. The inputs to the control unit is the ISA control sequences that are decoded in the control unit to generate meaningful set of control signals. Control outputs consist of halt or done type of signals to indicate the successful completion of an instruction. Control unit is also connected to instruction memory, from which it reads instructions and fetch them for execution. Control unit can be programmable or non-programmable. On the other hand, Datapad has certain inputs and outputs for data memory, where the data is stored for processing. We'll explore the details about these units in this class. So in our example, a data path consists of two building blocks, register file and a functional unit. The register file in this example, has 4 parallel load registers and 2 multiplexes for register selection and 1 register destination decoder. We would have, for example, 8 or maybe 16 registers as well in the next generation of this data path. So it's all design specific and it's in your hands. Here 4 is selected to be able to fit the data path within the limitations of the slide space. Register file has multiplexer B to select an external constant to enter the functional unit. Buses A and B are for address and data output. Multiplexer F chooses one of the operation inside the functional unit. It's either the ALU or the shifter operator. Multiplexer D is needed to choose either the output of the function unit or the data coming from data memory. So there are 4 status bits for that functional unit. They are for the ALU, in fact, V, C, and Z, where V is for overflow, C is for carry out, N is for negative, and 0 for the 0 condition. So here is an example. We select A to be 0, 1. So that basically places R1 on bus A. As you can see, I had these drawings on the data path to signify what's going on. Select B, set it to 1, 0, and also the MB is selected to be 0. So that will place R2 on bus B. When we set G to 0, 0, 1, 0, that would select G to have an addition operation. So bus A and bus B will be get added. And when we set MF to 0 and MD to 0, and in that case we place G on bus D, then we set the destination to 0, 0. And we basically enable the register file to place bus D contents on R0 at the clock tick. So that's going to store the result in the destination register. So there are also other micro operations that can be performed using the same data path circuit. So using the same circuit, other micro operations can be performed. For example, if you set MF equal to 1, you can shift or MB equal to 1, you can apply a constant, from outside. You can also initiate memory write by providing address and data load enable to, that is set to 0, and MD equals 1, for memory read. So basically, there are four types that is supported by this framework. It could be either register transfer microoperations or arithmetic microoperations such as addition, subtraction, incrementation, or decrementation. There are logic microoperations that are supported by the functional unit and shift microoperations. Here's the block diagram for the ALU. As you might remember from our digital systems class, it has a parallel adder section and a logic operation section. The least significant two select bits are used to select between different logic operations or arithmetic operations. The most significant bit select bit is used to select between the arithmetic or the logic operation for the incoming two n-bit numbers. The function table for the arithmetic section is summarized in bottom left of the slide. This table can be used to implement the B logic in the block diagram. This logic is introduced to be able to use the n-bit adder for performing 8 different arithmetic operations as seen in the table. The table details the appropriate inputs for that to happen. 0 and 1 in the table represent the all 0 or all 1 inputs generated by the B logic for the subsequent adder logic. Shifter logic of the functional block is used for different purposes. One of the main use cases is to perform multiplication and division operations passed. This slide shows an implementation of the logic shifter using multiplexers. You could alternatively implement it using different logic blocks. Shift select bits are selected to perform either the unchanged, shift right, shift left, or unused cases as summarized at the bottom of the slide. On the other hand, logic shifter is not good for sign bit operations. For correct operation, we need arithmetic shift that respects the sign bit. If you observe carefully, an arithmetic left shift multiplies a sign number by 2, whereas an arithmetic shift right or right shift divides a sign number by 2. Sign bit is kept while doing the right arithmetic shift, which is division. On the other hand, arithmetic left shift does not need to keep the sign bit. Yet an overflow can happen, and this can be detected using the logic shown at the bottom of the slide. Remember the similarity that this similar logic was used when we were talking about arithmetic adder operation in digital system design class. Here is the big picture of our Datapad register file. As I said, could have 2 to the m registers inside, and m bits would be enough to address them, where each register could hold n bits. And there are also, status bits like V overflow, C for carryout, and N for negative, and Z for 0. And that basically checks, for example, the negative checks if A minus B is less than 0, or 0 checks if A minus B equals 0, which means A equals B. This is the table for a given function select bits. The table summarizes the corresponding MF select bit, the G select inputs for the functional block, H select bits. We have also included in this table the set of microoperations supported by the Datapad and the corresponding function select inputs. From this table, you can easily derive the Boolean expressions for MF input, all G inputs and H select bits, as shown to the right of the slide. You can use, from your background, Kano maps and other background information that you obtained in the digital system design class. As can be seen in our Datapad, we generated control inputs such as destination source addresses, MB select, MD select, or RW select are all these multiplexer inputs which need to be controlled somehow. Finally, the function select, for example, must be provided to derive the data path for executing, a specific operation. So for a given microoperation to be performed, we need to generate a control word, which consists of ones and zeros, of course. Here's a table for different microoperations. As you can see, for some of the microoperations, some of the control signals have no effect. For example, an immediate add does not require an address for a secondary source register because the immediate value itself is the second operand. In that case, BA's, in our case it's the second source, BA's control signals is simply don't cares as shown in the table, and that helps us simplify the underneath the logic that is required to generate those control signals. Here's the overall picture of the single cycle computer For the single cycle computer example, we use two separate memories for both data and instructions. We didn't have to, but we just picked out that kind of approach. This is also known as hardware architecture. And if the memory was the same, you use the data and instructions for both of these information. We would have a von Neumann architecture. We assume hardwire control for now. As I said, we'll have more details on that. A PC here, program counter, is necessary for von Neumann type of stored program computers. And since ISA defines all the specification of the computing machine, next we'll discuss the ISA for the single cycle microarchitecture. There are three formats for the ISA: register, immediate, and jump and branch. The ISA is quite uniform. As you can see, the opcode, for instance, located at the beginning of the ISA code word. Register format is used to execute ALU operations such as addition or logical left shift, right shift operations. On the other hand, immediate is used to add a constant to a register content. As we, in fact, implicitly have seen that from the microarchitecture. But the ISA is kind of supported by the microarchitecture, and this is the format that supports it. ISA jump and branch instructions is a bit tricky and involved compared to the other two instruction formats, so let us spend a bit more time on it. Jump and branch is used to change the sequence of instruction execution. The AD field, which is AD stands for address, has two parts, left and right, and each of which is 3-bit long. An AD field can hold a 6-bit signed 2's complement number to be added to the PC's current value, of course, based on the contents of the register at address SA. So that's a condition that is stored in a particular address. It could have been, a zero check, or as we've seen in BRZ instruction, or negative condition, as seen in BRN instruction. There's also unconditional jump operation. In that case, the register at address SA holds the destination value, destination of PC value. In both register and immediate type instruction, the program counter is immediately incremented after the instruction is fetched. Since in this microarchitecture, status bits can affect the branch operation. First off, we need an enabler that is denoted as PL. If it is 0, the PC is incremented. Otherwise, it's either a branch or a jump operation. JB is used to differentiate between jump and branch. If it is 1, jump, otherwise branch is selected. To select between negative and 0 contents, we need another select bit, which is BC in our case. The table summarizes the explanation I've given you just now. So the branch control logic accepts all the status bits as well as the new select control bits, which are PL, JB, and BC. Using the instruction formats we talked about, it's of interest to tabulate all the operations that the ISA can support. The opcode determines the operation, if you remember. Here is the table. So this is the table for single-cycle computer ISA capable of executing a bunch of different operations. The new things that you might not be familiar are, for example, ZF. That ZF stands for zero fill operation. The M is basically the memory. So whatever you see in the argument is the memory value that is stored in a particular address. The SE notation is for sign extension logic. And then the table shows both arithmetic as well as logic operations supported by the ISA. It is usually best practice to look up the opcode or destination of a given instruction rather than memorizing it, and we will basically adopt this rule throughout this course. So here, some few example instructions stored in instruction memory for you to review. Of course, all instructions are in binary form. The format and the ISA determines the means and ways of interpreting these binary numbers stored in the memory. Please walk through each of the row of the memory that are at 25, 35, 45, and 55 to convince yourself that it's the right operation indicated in the rightmost column that the microarchitecture is performing. So if we combine the single-cycle computer data path with the hardwired control logic, we will finally have this circuit schematic. Don't worry about what hardwired control means at this state, as we will have more time to discuss two major control methodologies for computers in our next session. But here you can note that instructions read from memory are decoded by an instruction decoder. In fact, instruction decoder is the main logic of the control unit. If it is implemented using symbol combination circuits, it's called hardwire. So in our existing control word, we need to add four more, actually not two, but four more bits to complete the control word, and these are data memory write, which was absent in the previous version, and PL, JB, and BC. These are the control bits for branching and jump operations. So 16-bit long instructions need to be decoded into 20-bit long control word. So one approach could be to use a decoding logic purely based on combinational circuits and produce the necessary set of control bits using logic gates. This might be a bit involved because of the possible combinations, but thanks to don't cares, we may end up with a very simple combinational circuit. The instruction decoder is used for this particular purpose. On the other hand, another approach could be to use control memory and store all the control words inside of that memory. These control words are also known as micro instructions. So later, you can pull out the necessary micro instruction or micro instruction from control memory to send control signals to the datapad. So that's called microcoded control. We will have more discussions on that in the next session. So in this class, we covered a single-cycle computer microarchitecture. We talked about basic building blocks of a load store model, register file, and a functional unit. In general, we start with ISA and computer specifications before we attach, the implementation problem to that big, the general picture. The ISA is first presented after ISA is presented in this session after the microarchitecture, but in reality, the order is usually reversed. According to ISA specification, we have seen a design of functional unit, introduce you to the hardwire control, and the next class, as I said, we will focus on multi-cycle computers and two control model approaches to both single and multi-cycle computers. So please feel free to drop any questions you may have about today's lecture into my email box, and I'll be more than happy to help you with your questions. Thanks a lot.